Okay, so we almost halfway through the course. We haven't started any project work yet, right? I thought you guys should start thinking about it, but really, we haven't done anything. So we talked about what the data analytics need, the sort of concept, the sort of technology that comes with it. And again, the big data technology stack is not really covered with start because you won't be able to do any kind of Hadoop or Spark programming or anything. And chances are, unless you're in a big organization, you won't be okay. You won't be handling that. And even if your organization has a Spark system, they'll have a real computer engineers or IT specialists doing it. Yeah, so it's not really your thing. Your thing is more about trying to leverage off the power of analytics to analyze data, right? Okay. So, how do you analyze the data, right? Well, essentially, I can say, roughly speaking, we have really two tiers of tools. Yeah, one is the statistical tools, very traditional tools that you learned from last year, year one, right? That's when you make a lot of assumption about what the distribution is like, and then you gather the data, the statistical fit, you try to get the best fit. Yeah, but you make assumption on what the data distribution is. Well, machine learning comes in when you cannot use the statistical method. In other words, they have a nice distribution shape that you are prepared to deal with. Okay. So once again, you will not be. Once again, you will not be using machine learning techniques to analyze the data if your data satisfies statistical probabilistic assumption. Yeah, so that's the name of the game. So you try to use statistics method first. If they don't fit, then you have to go to machine learning types of approach, which is what we're spending a lot of our time in this class doing. Yeah. Now, today, well, here's sort of like a midway. What I want to do is kind of like review the whole thing that we've been going through, sort of like a pre-midterm review, yeah, as well as two things that I need to cover today. Again, I'm waiting for the pen. Yeah. So one thing that we need to cover a little bit is the notion of eigensystem decomposition. That comes in very handy. So this is something that we didn't have enough time, or we didn't have enough coverage during the statistical method, and so I have to. Can you guys stop doing that? Very distracting. Okay. So the eigensystem decomposition is very much the subject of linear algebra. So we cover it in the foundation class. I think maybe second or third class. Okay. Again. Okay. This is the data analysis, right? And you're going to want to draw. This is where statistical method is. It's a slightly smaller type of problem because it requires a lot of assumptions. Okay? And this is where machine learning comes in. Now, even though machine learning is larger than this, any problem that can be done in the statistical method just like in the here. If the problem satisfies the assumption that the problem is here, if you be smart or you be silly, just machine learning. You be silly, right? Because this method has a lot more information. It can tell you confidence intervals, it can tell you you can do hypothesis testing, you can do all kinds of stuff. Yeah. So if the problem satisfies this, for example, some kind of normality assumption, some kind of linearity assumption, some kind of distribution shape that you can apply. Then you have maybe you can learn about 10 different probability distribution in your first year and get paid nicely if you use that. Okay, you have to get it done. Okay. So I'm going to cover a little bit, not only in terms of the coverage that problem that can be handled under the statistical method is the way subject of those that can be handled by machine learning. But there are also types of problems that tend to be over here. So maybe certain class of problems are a little bit more here, a little bit less here. Some class of problems are a little bit here, more here, less here. Okay? And that's what the mind map is going to point out. Okay? So some problem is a lot here, a little bit here. Some problem can be a little bit here. Okay? And that's gives you sort of like a mind map of when you go to real life. Now the project in this class, obviously, since we have already done this in the first year, the project in this class will be those that we that's the side. That's the approach. Now, okay. So, can you guys see this? Let me make it a bit smaller. Okay. Oops. So this is where we are, machine learning. You have this, I'll load this for you guys. So you're not going to do statistical method in this class. Yeah. But the thing that you need to know, or you ought to know, is the difference here. Okay, this is what I want to communicate. Okay, the statistical. So in a way, if I ask you like a conceptual question, like is statistical method more powerful or less powerful? You can say both. You can say it's more powerful because it has a lot more information. It gives more analysis, more detailed analysis on the data that you analyze. It's also less powerful because it addresses a smaller class of problem. Okay. We're talking about data analysis, right? We're talking about data analysis. Okay, so consider this. Part of it is a review. Part of it is a perspective on machine learning versus statistical model that I want to address here. And then we'll go over, once we've done this kind of review, we'll go over to the second part of supervised learning. This is what we need to do, and we'll do a little bit of eigenvalue decomposition again, because that's quite useful, even though it is from linear algebra. And then we'll discuss the project, and that'll be today. Okay, good. So consider this. We'll start with sort of like a midterm review. Okay, you know this thing of the concept of the data, right? The data. What's the definition? Okay, some kind of measurement, some kind of record. It has to pertain to what? If you're just trying to read your mom, you report what kind of food she likes to eat, what kind of color she likes, what time she gets up in the morning. That's not really data because you already have that information. That's about your mom. You already have that information. So if you're trying to make a product that targets at an elderly lady, and then you record those information about your mom, then yeah, then it becomes a data point because your mom then is just a representative of a larger population. Yeah. So data in this sense, yeah, it is a record. It is a record, right? It is some kind of measurement, but it pertains to only specific sample of the entities. Okay. of which the general population is what you are interested in, is what you want to analyze. So the objective is to analyze the population, right? But before you analyze the population, you have to get sample entities from that population. Then you make the measurement, and then that becomes your data. Okay? Yep. Okay? Okay. Now I put here not only population but also phenomenon, right? Because instead of collecting data about your mom, and your mom is one data point representative of elderly ladies, okay? So you can collect your mom's friends' information. That becomes the second data point. And so what your mom and your mom's friends are that specific sample entity belonging to a larger population of elderly ladies. Okay? And you try to make some product that address that need. Not only do we have population in that sense of really population of PhDs or population of clients, you can say population of phenomenon. Okay? So phenomenon would be like price movement, flood. Okay? This you're not collecting flood. You're not saying, okay, let's put one flood here, one flood over there. No, you collect information on past events, right? So that you can infer, you can analyze a bigger population. That population is the population of all possible floods. Okay? So it's not population, it is phenomenon. Same thing with if you try to analyze stock price or equity price in the history, using historical price to analyze or predict the future price, the population is the population of all possible future price. So it's only not population in that sense. So it's phenomenon. Okay? So again, data fundamentally is a measurement or record that pertains to specific sample, specific entity. Okay? That's part of a bigger population or specific event, like the actual value of stock price today event that belongs to a bigger phenomenon, price movement. Specific event, how much is the flood damage this year that belongs to a larger population or larger phenomenon of flood anytime in the future, right? That you want to analyze. That's what you want to analyze. Okay. Now, what makes you different? What makes you different? Here, this is what I'm using in person. Okay, this is where the big data comes in. Okay, remember there are three kind of big nest. That's the V, right? V for volume. It's big because there's a lot of them, right? It's a lot of them. Well, you can have a lot of statistical data as well, right? That's not the problem. Okay, you can have big in the sense of fast velocity, fast. You need a lot of really high response, low latency computational platform, right? To do that. But the V, that statistical method that's not deal with, is the V for variety. Right? Now, it can deal with statistical method can deal with a categorical variable. That's not a problem because you can turn categorical variable into what? Into number. What kind of number? Nominal, ordinal scale. Okay? So those statistics you can handle. If it's something more informational, like more continuous values, right? Your height, your weight, temperature, then that belongs to the decimal and ratio scale. Okay? So all those are okay. Okay? So okay, you still can deal with that. But if it is something like text that has semantic meaning, picture, right? Picture is ultimately number, but the meaning is not in the number. The meaning is what it represents. Represents dog, represents cat, audio file. So those goes under all kinds of ก็เหลืออันนี้ก็ยังอันนี้ต้องอยู่นะอ๋อโอเคอันนี้ไม่ได้เดี๋ยวไว้ข้างไว้okay yeah so most of the time if it's tabular data things that are in Excel that it's created in statistical method. But of course, in our problem, that we deal with tabular data as well. Okay, so in this class, chances are the project that you're dealing with, okay, may not go into this kind of big variety unless you're dealing with sum, unless you're dealing with data, which you may. Okay, I don't recall exactly the original survey of the topic of interest. But if say like medical imaging, if you're interested in medical imaging, then you have to come over here, right? But if you're doing some kind of like a factor analysis, prediction, then it's still kind of tabular type thing, yeah? Now, population in this case, it means how do you generate the data, but never mind, okay? So that's basically the data bit that we talk about. So all of this really is in your interaction with the textbook. I'm just using this as a review, and I think when I give it to you, what I would do as a review for research is to actually go through this stuff. Okay, but if you click on a point, you click on something, right? Say something like that. Discrete value comes from what kind of scale? Comes from nominal, ordinal, and you say that. Or when I click onto the continuous, it comes from integral ratio scale. Then I can make a statement. So this is how you would do. This is sort of like my mental map help to organize concepts. So that's kind of review thing. Okay. Now, but here is where I think we deal with qualitatively different between statistical methods and machine learning, not only in terms of application, but in terms of how the computation works. Yeah, with in the quantitative data analytics, the model is data driven, but the raw data kind of enters slightly differently. Yeah, you remember I told you about the calculus, right? Calculus, there's like a very nice shape of error function, yeah? You know where the minimum error is, yeah? And that's what statistical formula is all about. Whether or not you're doing linear regression, whether or not you're doing, you know, maximum likelihood estimate, all kinds of stuff. Say that if I know what the data, if I get the data, and if I do the formula, and get the minimum error, it's kind of effective formula. It's a one-shot thing. And it's a one-shot thing, why? Because you make nice assumptions about the error surface. Yeah, you make a nice assumption about error surface. So mathematically, use calculus, just identify what's the resolution. The resolution is the one at the bottom of the error surface. Okay, it's a very nice error surface. So you can identify this point. But plotting something from the data set, right? In the formula, immediately I get the perfect solution. The best I can get from that moment. So in a way, this is the critical bit that I want to show. It's fed to a formula. Literally, it's fed to a formula. Okay? You have linear regression, and you have the formula for the coefficient. You have the formula that allows you to put in all the data and have x, y pair. Right? Once you put in the x, y pair to the formula, you get the coefficient. You are done. Okay? But in machine learning, it is an algorithmic process. It's an algorithmic process because whereas, okay, you know where this is, you just go over right there. That's the statistics, right? But again, machine learning, it looks like that. Okay, we can make it a little bit darker. The error surface is a little bit like that. But if it looks a little bit like that, and you knew what it looks like, you can also say, well, we need to go here, right? The problem with machine learning is, not only does it look like that, but what? You only see around the wall. Yeah, that's why you have to do this gradient descent. You look around, it's like going down the mountain to the bottom of the valley. That's maybe bottom, all bottom, two bottom, right? But even if it has all bottom, the point is you don't know where to go because all this is in the fall, right? In the fall, all this is in the fall, so you can't tell where it is. Now, let me make this point even clearer. Even if the error function looks like this, yeah, if the error function looks like this, can you go in one shot? Can you go in one shot? You can't, because you still stand here and looking very locally. Okay, so you still have to take a small step. Okay. Now this is easy because once you get to the bottom, you take another step. It's too big. You come back, then you're done. So it is easier. I'm not saying it's not easier. It is easier than this, but you still cannot do it in one shot. You still cannot do it in one shot, right? It's algorithmic. Algorithmic means give you a procedure, step by step, what to do. By the way, what was my algorithm? Look around, find the slope, go in the direction of the steepest slope downhill, take one step of some size. Look again, repeat until you look around and everywhere you go is uphill and you stop. That's the recipe. Yeah? It's much like you're frying an egg. Say, put an egg in the pan or scrambled egg, stir, check if it's no longer running. Yeah? If it is still running, stir, check. Is it running? No, it's still running. Stir, check. Then finally, there'll be a step where you check and it's not enough. So you scramble egg. That's an algorithm. An algorithm is nothing more than a recipe. Yeah, but it has this kind of loop, kind of procedural. Do until you the same loop. Yeah. So it's very important that the data is driven, but it's driven in a different way. Machine learning has that. Now, that's the one that say, I would, by the way, take advantage of this slides and go to look at even the statistical thing. Yeah. Now, where's the one that say analytical analysis? Okay, this one. Yeah. By the way, this is probably the most important thing I want you to take home in your mind map. Okay, this analysis here. Now, okay, let's do one thing at a time. Okay. So, first thing first, what's data? Data is the report of measurement of sample of entities or specific events that belong to a bigger population, belong to a bigger phenomenon. And it is the bigger phenomenon, it's the bigger population that you want to analyze, right? The keyword is analyze. So that becomes data analysis. Now, in terms of analysis, then this part says what kind of analysis can you do? Well, roughly speaking, there are three kinds of analysis. Yeah? There's one is to model the system first. So this is the model that allows you to do the analysis. Okay? And talk about it. We have one model. Okay? You can only analyze a system if you make a toy model of it. That's what the model is. Yeah? Right? So yeah, we want to do analysis. But before we do analysis, we do analysis. We must ask a simple question. The way you do analysis is to say, what happened if you do this to the system? Okay? What is the probability of this? Blah, blah, blah. So the model has to be built. Okay? So data analysis in this case means data analysis with the model that is already fit against the data. Okay? So that's very different from something like infographics. Graphical visualization, right? Graphic visualization, you get the data, you plot it, and that's your insight. Your analysis is done. You don't have to build a model. You just look at it. You look at the distribution. You say, oh, wait a minute. What are my customers? My customers, more boys or more girls? Look at the data. Plot it. Oh, more boys. Oh, so I have to sell more boys. And so you don't have to build a model. You build more girls, right? In our class, whether or not it's statistical method or statistical model or machine learning model, it is a model. You have to build a model. Yeah? So whether or not it's here or here, you have to build a model. Yeah? Now that's what's called model building or modeling. Okay? Now, I mentioned that there is this thing called optimization model, meaning that once you got a model of how things work, you can say, set a criteria. How can I get it to work the best? That would be the optimization model. Okay? Or you have a dynamic behavior, like a traffic or something like that, and that's how you already have a model of how that works. Your objective is to make sure that it doesn't get out of control, kind of in control. So that's the optimal control. Now, these two things are very important in your future because a lot more problems will be formulated this way. But in our class, we tend to focus with this first. Because after all, before you get to optimization, you have to know what the model looks like, right? And before you try to keep things in control, before you say, oh, let's keep the high economy in control, so that's what the active gradient, or you say, let's keep the traffic in Bangkok in control, so it doesn't become too congested. You have to have a good model first. Okay, so our focus is over here. Our focus is in the modeling part. Now, what do you want to do? What do you want to do when you model something? Okay, well, in a way, you want to gain insight. Okay, insight. And there are two kinds of insight that you can kind of think about building. One is called, where are the X's? The other one is called, you write the X, you know why. Okay. Now this is the distinction I want to get at. If you're interested in where are the X's, a lot of things here. Okay. Where are the X's? Yeah. It's traditionally addressed with statistical method because statistics has been around for hundreds of years. And if you go to Wikipedia page and look up probability distribution, there are hundreds of different recipes of broad probability. Okay, maybe we learned 5 last year, but there are hundreds of them, right? So you can take any kind of data, say like a histogram, you can check the histogram. My bet is traditional statistical method would find you a best fit. So we talk about where are things, okay? Where are things? Now, the difference is this. The difference is that sometimes where are things are not together. So there's some kind of natural cluster, right? So where are things tend to be forked out into two kinds of things. One is distribution analysis. So this is where statistical methods are to say for distribution analysis, I'm going to say that mostly statistical method. Mostly. Rarely do you need machine learning. Rarely. Okay? And on special cases, we do this thing called data mining that I told you about. Data mining is kind of a funny thing. It's not exactly machine learning, but it's not exactly traditional statistical method. Yeah? You don't have to write this down, by the way. Well, it's good to write down because that helps your memory. But you'll have this. I'll give this to you. Okay? But if where are the x's, it's not something like this, but a little bit over here, and maybe a little bit over here, a little bit over here, yeah? Or in two dimensions, instead of one block over here, we got 2 blocks, 3 blocks, 4 blocks, right? So this is kind of like what? It's kind of clustering. Now this kind of clustering is where you tend to go to the so clustering, okay? This picture is the time aspect. Okay? So if you go to things like distribution analysis, yes, most of the time. But if it's cluster analysis, most of the time you have to do machine learning. Okay? Right? And we talk about k-means or something like that, right? I think a while back. Okay? So that's just an example. So if it's cluster analysis, the picture is opposite. Generally speaking, it's machine learning. Occasionally, we use traditional methods. Then there are traditional methods, mixed model or something like that. But not very often, occasionally. So the picture is the other way around. So once again, start with data. Data is the basis for which you can get insight on the bigger population, bigger phenomenon that you want to study. Now, to get to that, you don't just say, my mom is exactly what everybody looks like. And yeah, or every elderly lady is like my mom also said. We have to make it kind of deep, right? From the small set to the big representation. That's what model building is all about. Model building is built on the data. Okay, but we have to have a separate model. Can have a publication that say, what does my mom like? Or what color does my mom like? Or what color does my mom's friend like? You have to have a model that say, what color does a typical lady of which my mom and her friends are? What color do they like in general? Okay, so you have to build that model. And again, the model, technically speaking, comes in three parts. One is this model itself, the model. The other one is the model that allows you to say, what is the best? What is the best? So that would be like a, again, logistic model, risk return, financial investment model. And then you have a model that says, let's keep things equal. These things are very rare. So these things keeps high economy between hyperinflation and deflation, keeps vehicle in the middle of the road, so that's kind of optimal control. Now, our focus in this class, right, because we are focusing on analyzing data, we're not building models. Right? These are things like, well, what can data tell you about the system? The thing that we're trying to model, the population, the phenomenon, we're trying to. Okay. Sometimes I use this word interchangeably. Instead of saying population or phenomenon, I would say system. Something. System. Okay. And again, model building. Once you have a model, it's the model that gives you this kind of clarification. What kind of questions you can ask for that model? If you can ask things like, where's the population? What does the phenomenon look like? And then it depends whether or not it's kind of homogeneous. If it's homogeneous, then it tends to be distribution analysis. Okay? This is my population of my homogeneous, right? But what shape is it? I don't know. Maybe it's normal shape, maybe it's student's T, but you know, for whatever shape it is, chances are your statistics will cover it. Because there are hundreds of different shapes. Yeah? You go to Wikipedia, you go to your last year's textbook, and you say, okay, well, let's pick this one and see if it fits. It's fine. Yeah? But if it's not always here, if it's little lumps of goes over here, goes over there, different segment, market segmentation. This kind of thing, yeah, statistics, traditional statistic distribution can handle, but not very well. Not very well. Not very well. Things like machine learning. Again, machine learning is an iterative, algorithmic way. So you do something. A good example would be what? The K-means algorithm, right? You might be, the data is not everybody together, but there are 3 lumps of you, but I don't know where the 3 lumps are. So I start with 3 random lumps, yeah, and I assign a cluster around that center, yeah, and see what the distance is. It's not good if you want to move the center of the lump and see the distance of those people with the lump of course, right? Keep doing this, keep moving this until I get to the end, right? I get to the end. Okay, so this algorithmic learning, this kind of machine learning is very suitable for this kind of problem. So that's why I say, generally speaking, when you go to cluster analysis, it's generally speaking, we're talking about machine learning. Okay, and here you can fill in the name of the technique. Maybe clustering, maybe that. And this is something that will be fleshed out in your project if your project focuses on clustering. Okay, so now you just learn about. I think I may have taught you just one clustering. That's a very classical way of thinking about clustering algorithm. If your project gets into clustering algorithm, then it may be worthwhile exploring other algorithms like it. Now you know K-means. Yeah, now you know K-means. Okay. So, model building. Now, how about this? Well, before I go on, clustering analysis in terms of machine learning, that corresponds to one machine learning paradigm. Yeah, I don't have the right answer. I just have data and I have criteria. Criteria is included. But I don't say that you belong to this group. You belong to that group. Yeah? This is general grouping. So what kind of learning is it? What kind of machine learning paradigm? Because I just said that most of the time cluster analysis will be handled not with last year's material, which is statistical method, but will be handled with this year's material, which is machine learning. But this year we're learning a lot of machine learning, right? So in this case, it's what is an example of kind of paradigm? Unsupervised, right? Because it looks like what babies learn when the babies try to put things together without being told what the right answer is. Yeah, so it is. So kind of machine learning, I just put maybe in particular, okay, unsupervised. I should put it learning. Okay. By the way, once you have this file, you can certainly edit to your own liking. So that's a clever way of using this. Okay. You notice I haven't used any PowerPoint at all. I use this thing. Yeah. Okay. In particular, unsupervised learning. Okay. Now let's go to this kind of model. The model that allows you to say, well, somewhere things are. How about I knew? Yeah, I knew one aspect, one dimension. Can I guess the other dimension? Okay. So where things are would be the distribution of height. thing, can I guess the other better? That would be something like, if I knew the person's weight, can I guess his height? Or if I knew his height, can I guess his weight? Right? Some kind of function. But it has this kind of function-looking thing. That's kind of function. X predicts Y. If X, then Y. X causes Y, only X is correlated with Y. But somehow it will really work it. Yeah. Now, this is very important, by the way. This doesn't mean that height causes weight or weight causes height, right? It just means that we do height first, making a weight. Yes, it's height, right? But it's not one causing the other. It's just information. So if you want to think about causation, it is information that is caused. Yeah, knowing X causes you to have better information about Y. But X doesn't cause Y. Height doesn't cause weight. Weight doesn't cause height. Yeah, causation and correlation are not the same thing. You can always do this kind of big data search, and you can say correlation between happiness and hair color, or something like that. You can always do this kind of correlation. The point is that in terms of research, oh, I want to be happy, so I'm going to dye my hair brown because correlation-wise, brown people are happier or something like that. That has nothing to do with it, right? Maybe it's something else. And this is, by the way, this kind of logical fallacy or logical correct logical deduction, I think should be taught at every undergraduate program. Not your class or anywhere. Engineering, liberal arts, science, art, we should be taught logical reasoning. Yeah, that's a now. So let's go to this guy. If I knew X, what can I say about Y? Well, that comes in two flavors. Yeah, that comes in two flavors. One flavor is called regression analysis. One flavor is called classification analysis. And they are, in a way, similar. Give me X, I'll give you Y. If you told me X, I'll guess Y. The more I know about X, the better I can tell you about Y. Okay? The difference is in what the target variable is, right? If the regression analysis, you're applying on what? Well, if it's regression analysis, what's the target variable? What's the Y? The Y would be something that's continuous, right? And therefore, it comes from what kind of scale? We call a ratio, right? Height, weight, example, you said, I'll give you your height, I'll guess your weight, I'll give you your weight, I'll guess your height. Yeah? What about classification? Well, classification is discrete, right? Not A or B or B or B. So, what kind of number scale would that be from? Okay, is discrete, what kind of scale comes from? Ordinal or normal, right? Now, the exception case would be occasionally, you would use regression for ordinal. Occasionally. The ordinals are funny things. But anyway, I want to tell you this. If it's regression analysis, the distinction between statistical versus learning is not like this. It's not static. It's more like this. It's more like once upon a time, regression analysis is done here. Once upon a time, regression analysis. Nowadays, it's done here. Yeah? So it's not a lot like this. Literally, it used to be like this, now it's like this. Regression analysis used to be done with traditional statistical method, but more and more it's becoming. So I can't draw you a static plot. It's sort of like a movie plot. You can see a lot in here, but now it's outside. Yeah. Now classification, again, it's similar. Classification is a little bit like that as well. You know, once it's usually here, now it's kind of out here. Yeah. The data mining, I guess that's a special case. Yeah. So once the norm, but now. Yeah. So yeah. So both regression and classification, it's kind of like this 20 years ago, but today it's like, the reason I don't use exact same word is because, you know, there's a lot of traditional statistical method that still stand. For example, metrics like national economy, like modeling GDP or something like that. Then the relationship is so well founded that it's still stable. Yeah, but probably not for you guys. Yeah, for econometrician, for economists, right? Doing something like predicting GDP given the past inventory number, given the past capitalization rate, and all that kind of stuff. Then traditional statistics, in particular what's called econometrics, still work really well. But probably not for you people. Yeah, not for you guys. Good example, I think good example is my own experience. I spent a lot of my career in credit risk modeling. Well, credit risk modeling used to be something like, well, what's credit risk modeling? Usually some kind of loan approval, right? Loan approval. So it's kind of like a classification. It's a guy I'm going to lend money to and a guy I'm not. Okay? And it's a binary classification. If I'm going to say you are likely going to be bad, yeah, you're likely going to be bad. So I say, yeah, I have a model that is very whether or not you're going to be bad. So 1 for bad, 0 for good, or not bad. Yeah. So it's a binary classification, right? Binary classification. Now, the old days, 10 years ago, 20 years ago, banks would do this. Banks would do linear regression on the income, the education, right? And once you get all this weighted sum, you put it into a logistic function under logistic regression, and if the value is equal to 1, the value is equal to that. If the outcome is close to 0, then I think you'll be okay. You will not be bad then. Yeah. So traditionally, that used to be like that. Alright? But why? Why don't we do it anymore? Because that logistic regression is equivalent to 1 neuron. Right? And now we have neural network, which is 1,000 neurons. So it's a lot more powerful. Much more powerful. And I show from mathematics, yes, I don't want to spend time showing it again, but you see that, right? If 1 neuron was separate like this, 2 neurons can make a very complicated surface. Now imagine 1,000 neurons. I can make it very complicated. Right? So nowadays, I'm going to do credit risk analysis of potential borrower. I'm going to do it over here. So from logistic regression becomes multi-layer perception. So this is the logistic regression base. Now it's multi-layer perception. Yeah. The multi-layer perception will take over now. Yeah. Right. So that's the sort of analysis you do. Now, so that's my way of review. Now, the other thing that the model does is kind of the opposite, but I'll just give you 2 words about it. It's called solving a problem. Solving a problem is a little bit different from modeling. It's trying to find the inverse. If you think about it, if you say ax equal to y or y equal to ax, that's building the model, right? Y is equal to ax. But if I ask you to solve the equation, solve the problem, if y is equal to ax, right? Y is equal to ax, and y is equal to 7, what x? That's kind of like inverting the problem, right? Okay, so this is a model. My model is y is equal to ax. My model. Okay? If I ask you to solve a problem, it would be something like, well, I'm thinking of a y. What's the x? So x is equal to y divided by a, or a equal to y. Okay? So that's sort of like inverting the model. But I'm not spending a lot of attention here. You know why? Because it's more relevant for optimization problem. Because in this case, you don't want any y, you want the best y. Okay. So this kind of inversion, this kind of find me the best, find me the x that gives me that y. And this kind of model tends to be more relevant in optimization. If I have this kind of strategy, this kind of market, it gives me this profit. If I want not just any profit, I want the best profit. Yeah? That's my Y star. What is my X star? What's the best X star that will give me that Y star? So that tends to be a lot more relevant in optimization. Okay? Now you guys are more at the level of building a model and understanding. Okay, so it's more modeling, so I'm not going to spend too much time on it. Okay, good. Now, basically, this kind of analysis engine is to put all your the universe of your knowledge together. Okay. What kind of tools do you have? You have things like visualization, and that way you don't need to build a model, right? Because once you get it, yeah, once you get it, but you don't have to do the model. This is the point I want to make here. With interactive visualization, as the analysis, it is the analysis. Once you make it plot, once you make it visual graphic, you don't build a model. You show that that's your insight. So in that case, visualization is the analysis, right? Is the analysis. So as an engine of analysis, as a tool of analysis, yes, it is the analysis because the insight is immediate. Once you see this kind of picture, you get it. You know what's happening. The insight. Now, vis-a-vis other more complicated engines, visualization is also important because sometimes the visualization, not sometimes, most of the time, the visualization is what informs the model. So don't think of visualization as alternative to your machine learning or statistical method, right? You get what I'm trying to say? Yeah. As an analysis is to make insight, right? As a competitor, okay, let's put it out. Yeah. Visualization can be a competitor to statistical method and machine learning when the situation is simple. When the situation is simple, you don't need to build a statistical method, statistical distribution model. You don't need to build neural network. You don't need to do anything. You just need a visualization. So it's kind of like alternative or competitor because it's done. Once you've done the visualization, you get the analysis, right? You get the insight. You're done. But most of the time, visualization is not enough. But instead of saying, well, the visualization is not as good as statistical method or machine learning model, why do visualization at all? It's because visualization helps you build the model. By looking at the data By visualizing the data, it tells you, well, this is a problem that is homogeneous distribution, so let's go to statistics, or is it sort of like different cluster? Remember the old geyser, right? The old Facebook geyser? By looking at the data, visualizing the data, it tells you that it has two nodes, right? Okay? So it's multimodal distribution. Now, if you don't look at it, you don't visualize it, you can do all kinds of statistical tests, blah, 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 and it's going to take you a while for you to realize that you need to operate it in population. But by visualization, it tells you right away. Just looking at it, just looking at it. So that's why histogram, scatter plot, all kinds of things are extremely important. Help you build the model. Now, the other end is also important as well. Once you build the model, and this is something that I do daily for my project. Once you do the analysis can be numerical, it can be very complicated, it can be very technical, something that I understand. But if I want to use it in my something like that, I have to visualize that. So it's not visualization of the data, but visualization of the result of my analysis. Yeah. So that's why, as a competitor, it's only for a trivial case, but as a complement, yes, it's very important at both ends. In the beginning of the analysis, before you build a complicated sophisticated model, and at the end, when you get the result, you want to show, make it intuitive, right? So visualization is something that that you should have. Now, I'm making this point here. One is telling you that regardless of what the project will be, the project will be clustering analysis, the project will be building multi-layer perceptron convolutional neural network, you will still rely on visualization. So, and I'm not going to well, unless you have some really interesting project, visualization is your project. That's possible as well. But chances are visualization will be part of your project. It will be the beginning part where you use it, analyze the data. It's the end part where once you analyze the data, so visualization is that important. And that's why I can use this Mathematica manipulate, because not only is it calculating, it's giving you the visualization, interactive visualization. And again, we have this kind of class, machine learning, statistical method, data mining. I kind of like stick it in the third category. That's what I think. But you know, some people would do this. Some people would say data mining is part of statistical method. Some people say statistical method, data mining is like precursor of machine learning, so it's over here. But I kind of like put it over here. Yeah. So this node, okay, when you go to introduction, yeah, introduction. This is there are three branches to the introduction, right? About data analysis, statistical method, and machine learning. This will be a good review of what you should have learned last year, right? This is what we learned this year. And this is a perspective on how they both combine or how they apply to data analysis. So that's important. Now, from our point of view, yeah, from our point of view, we did this. This is what we did. We say some kind of machine learning, right? Machine learning. How do you define it? I define it as machine plus learning. What's a machine? It's something that's assigned to a task. But this kind of machine doesn't just get one task. It's not like a canning machine that cans fruit, right? That thing just does one thing. It doesn't matter if you want it to do. And then it's programmed. That's the program. A learning machine is not programmed to do something for you. It's programmed to learn first. So that's the critical part, right? Critical part, right? If I have a assembly robot in a factory, right? And I make a specification. I want the robot to make this kind of things, I'm programming it, right? I program the machine to do this task. But in a learning machine, what I program is, I program the learning task. I program the machine to learn from data. And that's this part of it, this output. It's only once it has learned, only once it has learned, can you do another task. So it's a little bit more like human being. Before you are useful to your parents have to teach you how to walk, how to talk. Before you used to go to a company, to a business, you have to learn how to make data analysis, how to learn how to build machine learning model, and that's what this class is. So this is your learning path. This is your learning path. In college, your learning path. Shortly after you have done your learning path well, can you do the job task well? Okay, it's a two-step thing. So if you think of yourself as a machine, you are in a learning mode now. You're not in a performance. You're not doing anything. You're not doing anything. Right? The job is to learn. Internalize the knowledge. Read, book, decide, that's your job. The task is learning. So only after you've learned, you graduate, then you can perform something useful. Now, the idea about lifelong learning, of course, is the fact that you need to relearn a lot of things as technology changes, as environment changes. So if you only learn for 3, 4, 5 years in your college, maybe 10 years, say a PhD, and you don't learn anything else for the rest of your life, then you will become humble. So a human being has even another layer that machines don't have. You're not just learning something, you're learning how to learn. Right? So it's still better than a machine in that sense, right? A machine, it has to go through supervised learning, unsupervised learning, the learning path. But you're actually not just learning something from this side. Trying to teach you the discipline of learning. Okay? So you're learning how to learn. Okay? This is separate. This is not a machine. There aren't unless we talk about very advanced AI model. Then we don't talk about that. Yeah. Just talk about machine that learn from data. Once the machines learn from data, it's considered learned. It doesn't learn anymore. It's already smart. It's ready to use that. The job change, you just have to retrain it. You have to retrain it. It's like saying, if you don't learn how to learn and technology change, what happens? You come back to school. Machine is like that. A machine has learned the data set to do something. And if the environment changes, the data change, things change. The only way that the machine will be relevant is to retrain, to take it and relearn it. This is more supervised learning, more unsupervised learning. It's like going back to school. Okay? But hopefully, if you learn how to learn, for the rest of your life, you can learn without coming back to school. That's one thing. Okay, so you do the learning task first before you do any kind of useful task. This kind of performing task. The learning is algorithm. The learning is done through a process of algorithm, and the basis of algorithm. Now, this one I'm just giving you the context. There are machines that doesn't learn from data. It learns from some kind of hidden rule. There are machines that learn from simulated environment, learning machine that learns from environment. It doesn't learn from data. It doesn't apply to you guys, okay? So robotics, a self-driving car, things like that, learn from simulated environment, okay? It doesn't learn from real data. It simulates like a driving situation. Okay? So that's not real data. Okay? This is simulated environment. Okay. That's not you guys here if you're doing for analysis, right? For analysis, the basis of learning, what you compare your learning against, your performance, if you're learning well, is based on data. Okay? So it's data driven in that sense. Okay? That's saying machine learning is a machine, okay, that does the learning. How does it learn? It learns from algorithm. Okay. Now the other definition is go the other way, to go with learning first. What's learning? Well, the learning paradigm has three types of learning that a human baby does, A human baby that's learned by supervised, unsupervised, and reinforced, right? Reinforcement is when the behavior gets reinforced over time. Okay? That's a little bit far-fetched from the data application. So you deal with these two more. Okay? Supervised learning and unsupervised learning. So machine learning here in this case starts with the definition of what is the learning. And then what's the machine that does that? Well, that is just a computer. Okay? Now, I mentioned this just so you know, because in your lifetime, not in my lifetime, in your lifetime, in my lifetime, there's no competition. Right? The computing architecture is von Neumann. There's no, there's no, it's supreme. It's a computer that does everything from the day I was born, from the day I die. Okay? And would be the majority of the application. But if I don't die soon, or for your case, you have a lot of future ahead of you, the computing itself, the computing thing, the machine itself, will have a big player, a newcomer, and that's called quantum computing. Okay? It's a different story. Okay? And now, today, okay, 5 years ago, quantum computing became relevant. This year, people are trying to use quantum computing to learn. So it's quantum machine learning. Okay? So I think this future is getting quicker than I thought. So maybe it's going to come my lifetime. Okay? So this is what's coming. Okay? Well, the context, when you just look at that, and this is something that we did the first class. We did the first class of topics, that sort of thing. Okay? Good. Okay, so that's sort of like a review. That's sort of like a review. I haven't reviewed the specific learning technique, right? We talked about K-means. I just mentioned that a little bit, but on the supervised learning and in fact, I'm not going to cover that in the mind map form. I will cover that in the mathematics and in the so conceptually, you have to know the thing. So what is the story arc? What do you tell your parents that you learned in this class? Well, of course, talk about data itself. Start with the word data. Right? You analyze the data, you build a model. Okay? Last year, you already learned to build one class type of model. A model that is very good at learning distribution, is very good at problem that has certain features, linear, normality, all kinds of stuff. Okay? Set the limit theorem and whatnot. But if you want to do something that's a little bit tricky, even if you don't go to variety data, the picture, you have the data, you do more complicated. Okay? Just like before, now that trading is, you have defined. You have income, education, asset side, blah, blah, blah. You do this statistical model and you get a logistic regression. Now you got something more powerful because logistic regression is just one neuron. And calculate is just one kind of analysis. So it's much more, it's kind of like better than the old thing. Then, so that's why in this class, you are spending a lot of time here. Okay? So these are the tools, right? You say this is a tool, this is your first year tool, this is your second year tool. Okay? And the first year tool, you probably didn't spend a lot of time. It's not called data analysis, it's statistics. Statistics, because the data usually comes from the data. You don't need to talk great things about what the data means. Big data, small data, that sort of thing, right? You don't have to deal with that because it's always numerical data, right? It already comes from numerical data. In this class, because it really things that are, you have to have a bigger perspective. And also, now that you don't have this statistical method, you have this. You have to do the perspective of 2021. Yeah, 2021. Now, personally, it should be something like, I would prefer to use statistical method if I can. Yeah, the chances are, because you're in a new economy, you deal with social network data, you use pictures, you do that, you are not able to. By the way, final point is this. Remember this thing where I say that you have this visualization. The visualization is not enough, but it's still around. It doesn't help you. But you know what? What's going to happen in the future? Statistical method will always be around. And even when you can't use it, you will use statistical methods to describe the outcome. See what I mean? Okay, so visualization as a technique may not be good enough, maybe the inside, but it would inform you how to do it and it will help you to get the job. If you go to this next block, which is the statistical method, sometimes it's not powerful enough. So you need to go to machine learning, but you still use statistical method to help interpret results. And that's why we have this thing like receiver operating characteristics, table. These are kind of inspired by statistics. Type 1 error, type 2 error. Okay? So it becomes not a tool itself, but becomes a complementary tool to machine learning. The problem can work in machine learning, but when you present the result, you present it in terms of probability statistics. True, negative, true, positive, false, negative, trade-off, the ROC curve, area under curve. These are all derived from statistical. So you can see that the future kind of goes like this, and who knows? Maybe in the future, maybe something else will be here. Yeah? Right? Maybe there's something else over here. So maybe I should have drawn the picture that starts with something like a visualization or kind of a visualization or descriptive statistics. Then today, I don't know, maybe it's quantum machine learning. Yeah? That's where your lifetime, not mine. Yeah. So it goes like that. It goes like that. And you notice the case of humanity, the progress of humanity can be measured because of Excel adding. First, Excel just has the spreadsheet. Then it contributes the fact. Then it has regression analysis. In 10 years' time or in 5 years' time, the machine learning will be Excel adding. I think. Okay. It would be a bit clumsy. It wouldn't be as powerful or as intuitive as Mathematica. But my guess is that's how the Microsoft product strategy. Things that get more advanced, fucking. So we'll see what happened to Excel 20.